A galaxy cluster is hiding a collection of cosmic secrets that defy explanation. We are journeying millions of light years to the heart of the Leo cluster, a sprawling metropolis of galaxies, to confront 25 of its most profound mysteries. By the end, you'll possess a front-row seat to the cutting edge of cosmic discovery, where every answer only deepens the wonder. Here, we find galaxies that seem to run without dark matter, ghostly structures older than time, and signals with no known source. What do you believe is the universe's greatest unsolved puzzle? Floating in the vast emptiness between galaxies, a ghostly circle of primordial gas defies all expectations. This is the Leo ring, a structure so immense it could swallow our own Milky Way galaxy many times over. For decades, this colossal loop of cold hydrogen has orbited two galaxies, known as M105 and NGC 3384, presenting astronomers with a formation puzzle that seems to have no clean solution. The ring is simply too large, too symmetric, and too rich in gas to be the messy debris from a violent galactic collision. Those events typically scatter material in chaotic streams and shells, not in a near-perfect, coherent ring that has persisted for billions of years. So if it wasn't born from a crash, where did it come from? The first and most profound theory suggests we are looking at a fossil, a relic cloud of pristine hydrogen and helium that has survived untouched since the universe's first few minutes. In this scenario, the Leo ring is a leftover building block, a piece of cosmic scaffolding that never condensed into stars or galaxies. It is a direct window into the infant universe, a bubble of ancient gas preserved in the deep freeze of intergalactic space. The second major idea paints a different picture. Here, the ring is not ancient but newborn. It could be a tidal dwarf galaxy in the making, a vast structure of gas pulled out during a close encounter between its two host galaxies. But instead of fragmenting into stars immediately, this ring of gas has remained strangely dormant, a sleeping giant of potential that has yet to awaken. This theory is compelling, but it struggles to explain the ring's stunning regularity and stability. Why hasn't it collapsed under its own gravity or been ripped apart? Each explanation solves one part of the puzzle while deepening another. If it's a primordial relic, its survival in a busy cluster environment is a miracle. If it's a tidal structure, its formation was an event of impossibly precise physics. The Leo ring forces us to question the very narrative of how structure forms in the cosmos. Are we missing a fundamental chapter in the story of galactic evolution, one where serene rings of gas can appear as if from nowhere? This silent, circling enigma is our first clue that the Leo cluster operates by a hidden set of rules. But a ring of ancient gas is not the only structure here that defies the cosmic rulebook. Deeper within a sub-region of the cluster known as Abel 1367, astronomers found a galaxy that seems to operate without the universe's most fundamental ingredient. This galaxy, catalogued as NGC 1052DF2, presents a terrifying and beautiful paradox. It appears to have almost no dark matter at all. To understand why this is so shocking, you must first understand dark matter's role. Think of a galaxy like a grand, spinning carousel. The horses and riders on the outside have to move much faster to keep up with those near the center. In a galaxy, the stars on the outer edges should, by all the laws of gravity we know, be drifting away slowly, unable to hold on. But they do not. They orbit at tremendous speeds. For decades, the only explanation has been that galaxies are embedded within vast, invisible halos of dark matter, a mysterious substance that does not emit or reflect light, but whose immense gravity provides the extra glue to hold everything together. It is the unseen engine that makes the entire cosmic carousel spin. Now, imagine finding a carousel where all the outer horses are moving at a gentle, leisurely pace, perfectly content, as if the massive, hidden engine simply did not exist. That is NGC 1052DF2. Through meticulous observations, scientists measured the motions of 10 bright star clusters orbiting within this diffuse, ghostly galaxy. The speed of their orbit was shockingly slow. The math was undeniable. The amount of regular, visible matter in the galaxy was more than enough to account for the gentle gravity they felt. There was no room left for the signature of a massive dark matter halo. It was like weighing a car and finding its weight matched exactly the sum of its parts, with no extra mass hidden in the chassis. The implications of this are monumental. Does this single, bizarre galaxy disprove the entire concept of dark matter? Not necessarily, but it forces a brutal confrontation with our theories. One possibility is even stranger. Perhaps dark matter is not a featureless halo that always clings to galaxies, but a substance that can, under extraordinary circumstances, be stripped away. Could a violent event in the cluster's past have ripped the dark matter cleanly from this galaxy, leaving behind only the visible stars? Or does this point to an alternative form of gravity, a modification to the laws of physics themselves that works differently on such vast scales? This pale, ghostly galaxy is a profound outlier. It is a cosmic rebel that refuses to follow the rules, and in doing so, it asks the most fundamental question of all. Are we missing a piece of the universe's operating manual, or have we been reading it wrong from the very beginning? The silent rebellion of a ghostly galaxy is not the only way the Leo cluster smothers stellar life. At the heart of another seemingly ordinary galaxy, a supermassive black hole is conducting a slow, cosmic assassination. This is the red geyser, a phenomenon where the galaxy's central engine is not devouring matter in a violent, bright quasar, but is instead emitting a steady, focused wind of energy. Think of it not as a volcanic explosion, but as a relentless, high-pressure geyser of invisible force. This wind pours out from the galactic core in two opposing jets, sweeping through the galaxy's reservoirs of cold gas, the very fuel needed to birth new stars. The wind does not blow the gas away, it superheats it. It stirs the calm, cold pools of star-forming material into a hot, turbulent frenzy, preventing the gas from ever cooling down and collapsing into new stellar nurseries. The galaxy is not dying in a blaze of glory. It is being gently, thoroughly sterilized. Astronomers first identified this process not by seeing a brilliant beacon, but by reading the subtle signature of moving gas within a red, aging galaxy. Using instruments that can dissect the light from millions of light years away, they detected the specific Doppler shift, the fingerprint of gas being pushed at tremendous speeds by an unseen force. The source was traced back to the galaxy's core, where a relatively quiet supermassive black hole was, against all expectation, the culprit. This makes the red geyser one of the universe's most insidious killers. It explains a long-standing mystery. How do massive galaxies transition from their vibrant, star-forming blue youth into their quiet, red and dead old age without any obvious catastrophic event? The red geyser provides the answer. It is a slow-acting poison, a process of quenching that can take billions of years, leaving behind a galaxy full of aging, red stars and no way to make new ones. The dense environment of the Leo cluster, with its crowded galaxies and complex gravitational tides, may be the perfect pressure cooker to trigger these quiet outflows. If so, then scattered among its thousands of galaxies could be many such geysers, each one silently turning off the lights of star formation, one galaxy at a time. This reveals a hidden layer of control in the cosmos, where the most massive objects dictate the fate of their homes not through consumption, but through a whisper that echoes for eons. The silent sterilization of a galaxy by its own black hole is a process of profound control, but what about galaxies that seem to have no control at all? The Leo cluster is home to some of the most ethereal objects ever catalogued, cosmic phantoms that stretch the definition of a galaxy to its breaking point. These are the ultra-diffuse galaxies, and two of them, NGC 105 2DF4 and Dragonfly 44, present a pair of paradoxes that are mirror opposites of each other. They are both galactic ghosts, each as wide as our own sprawling Milky Way, yet containing only about 1% of its stars. If our galaxy were a bustling, luminous metropolis, these would be vast, empty plains under a sparse scattering of streetlights, so faint they were only discovered in the last decade with exceptionally sensitive telescopes. Their sheer size and dimness make them nearly transparent. Cosmic will owe the wisps floating through the cluster. Yet for all their visual similarity, their internal realities could not be more different. We have already met one ghost that defies the rules. NGC 105 2DF4 appears to follow its sibling DF2 in lacking the gravitational anchor of dark matter. Its stars move with a languid, gentle pace, suggesting the galaxy is held together only by the feeble gravity of the pinpricks of light we can see. It is a wispy cloud that should, by all rights, be torn apart by the tidal forces of the dense cluster around it, and yet it persists. Then, just a short cosmic distance away, floats Dragonfly 44. This galaxy looks almost identical, a vast, faint smudge of ancient stars, but when astronomers measured the motions of its star clusters, they got a shock. Those points of light were whizzing around at tremendous speeds, velocities so high that the tiny amount of visible starlight could not possibly hold them in orbit. The math revealed something astounding. Dragonfly 44, despite its ghostly appearance, is almost 99.99% dark matter. It is not a wispy cloud, but a colossal, invisible gravitational engine wearing a veil of a few stars. This is the heart of the mystery. How can two galaxies that look so similar, born in the same cosmic neighborhood, have such radically different souls? One is a phantom of normal matter, barely clinging to existence. The other is a titan of shadow, its true form hidden from view. Their existence forces a brutal question about galaxy formation. We thought we understood the recipe. Start with a massive halo of dark matter, let gas fall in, cool, and form stars. But here, that recipe has produced two completely different dishes with the same ingredients. Perhaps DF4 had its dark matter violently stripped away in a past encounter, a cosmic mugging that left it exposed. Perhaps Dragonfly 44 represents a dark matter halo that, for reasons unknown, failed to attract much gas to ever form stars, leaving it a nearly empty shell of pure gravity. Or perhaps we are seeing two different endpoints of galactic evolution, one where the dark skeleton is laid bare, and another where the luminous flesh is all that remains. These twin phantoms are a controlled experiment written across the sky, challenging us to explain why one ghost walks without a skeleton, while the other is almost nothing but skeleton. What hidden variable in the early universe decided their fates? The profound contradiction between the twin phantoms has ignited a firestorm in astronomy because they are not alone. Scattered in and around the Leo cluster are several more of these ethereal galaxies, each one a potential rebel against the cosmic order. This growing collection, a trio of dark matter-free galaxy candidates, has turned a single anomaly into a pattern that demands an explanation. Take the neighbors of the infamous NGC 105 2DF2, for instance. Astronomers, scrutinizing the same patch of sky with even greater care, identified other ultra-diffuse galaxies with similarly sluggish star motions. Each new candidate galaxy strengthens the argument that we are not looking at a fluke or a measurement error, but at a genuine new class of cosmic object. The community's response has been a masterclass in science in action, a rigorous and sometimes heated debate fought with data. Skeptics have launched a multi-front challenge. The most crucial battle is over distance. A galaxy's distance is everything. Get it wrong, and all your calculations about its size, its brightness, and most importantly, the intrinsic speed of its orbiting star clusters collapse. If these ghostly galaxies are actually much closer to us than assumed, then their star clusters would be moving slower than we think, and the need for dark matter to explain their motion vanishes. It would mean they are simply small, faint, nearby objects, not massive, distant rebels. Teams have sparred over the precise methods for measuring these immense distances, using everything from the brightness of red giant stars to the subtle properties of the galaxy's overall light. Each new paper brings a refinement, a correction, a new piece of evidence. The other major line of inquiry asks if they are real and truly devoid of dark matter. How did they get that way? The leading theory is as dramatic as it is plausible: tidal stripping. Imagine one of these diffuse galaxies, born with a normal dark matter halo, wandering too close to the immense gravitational well of a giant galaxy like NGC 1052. The encounter would be a cosmic tide. The invisible, spread-out dark matter halo, being less concentrated, could be pulled away first and more easily, like a loose cloak snatched by the wind. The more tightly bound stars huddled in the center might remain behind, left as a visible remnant sailing on without its gravitational anchor. This process could create the exact ghosts we see, galaxies of normal matter that have been mugged of their dark essence. This trio of candidates, therefore, represents more than just a list of oddities. They are the focal point of a living, breathing scientific mystery. Are they the result of a catastrophic stripping event, forensic evidence of a violent cluster history? Or are they something far stranger, galaxies that formed in the early universe without dark matter from the very beginning, challenging our most fundamental models of how structure coalesces after the Big Bang? Every new observation sharpens the debate, pushing our tools and our theories to their limits. In the crowded depths of the Leo cluster, we are witnessing a trial for one of cosmology's core beliefs, with the verdict still hanging in the balance. While astronomers debate the ghost stripped of dark matter, the cluster reveals a phenomenon of shocking color and life. Drifting alone in the Black Sea between galaxies is a brilliant azure smudge, a stellar nursery glowing with the fierce light of newborn suns. Astronomers call it the blue blob, and its very existence is a cosmic rule breaker. We have always understood that stars are born within galaxies, from the dense, cold clouds of gas that swirl in their spiral arms or collect in their cores. The vast intergalactic voids were thought to be sterile, empty deserts. The blue blob defies that. It is a pocket of furious star formation, 1,000,000 degrees hot and shining with the intense blue light of massive young stars floating with no galaxy to call home. How did this island of youth end up in a sea of ancient red giants? The first clue lies in the stars themselves. Their brilliant blue color is the signature of extreme youth and mass. Blue stars burn their nuclear fuel with a reckless intensity, living fast and dying young in spectacular supernova. The presence of so many in one place means this entire region ignited in a sudden, violent burst of creation, likely within the last few 100 million years, a mere blink in cosmic time. Their chemical makeup adds another layer of intrigue. The gas that formed these stars is not pristine, primordial hydrogen. It is enriched with heavier elements like oxygen and neon, the forged ashes of previous generations of stars that lived and died long ago. This tells a critical story. The material in the blue blob did not simply condense out of the empty void. It has a history. It was processed inside a galaxy, or perhaps multiple galaxies, before being ejected or stripped away. So what was the delivery mechanism? One compelling theory points to a galactic collision of breathtaking violence. Imagine two spiral galaxies, each with its own reservoirs of gas, engaging in a slow, gravitational dance that turns into a catastrophic merger. During such an event, immense tidal forces can wrench colossal streams of gas out into intergalactic space, flinging it far from the chaotic centers of the merging galaxies. This ejected cloud, rich with the chemical ingredients for life, could then drift for eons before something, perhaps a shock wave from another cluster event or its own inward collapse, triggers a spontaneous, furious round of star formation. The blue blob could be the glorious, isolated aftermath of that ancient wreck. Another possibility is that the blob is not a remnant but a refugee. It could be the visible heart of a so-called dark galaxy, a clump of dark matter that managed to attract a small, dense pocket of gas which then ignited into stars. Yet its isolation remains profound. It challenges the very geography of star birth, proving that under the right extreme conditions, the universe can light candles in the darkest, most unexpected places. This brilliant blue anomaly forces us to ask if the spaces between galaxies are truly empty, or if they are secretly scattered with these stellar oases, each one a testament to the chaotic, creative violence that built the cosmos. The brilliant isolation of the blue blob shows that star formation can ignite in the most unexpected places, but at the heart of a different, seemingly insignificant galaxy in the cluster, an even greater anomaly is hiding in plain sight. This is the story of an overmassive black hole, a cosmic monster that has grown far too large for its tiny galactic home. The galaxy in question is a dwarf spheroidal, a faint, diffuse collection of ancient stars, one of the smallest and most common galactic building blocks in the universe. In such a modest structure, astronomers expected to find, at best, a small black hole, perhaps with a mass of only a few thousand suns. The relationship between a galaxy and its central black hole is one of the most consistent rules in modern astrophysics. Larger galaxies with big, bulging centers host proportionally larger supermassive black holes. It is a tight correlation, suggesting that galaxies and their central engines grow together, locked in a symbiotic dance across cosmic time. But this dwarf galaxy, through painstaking observations of the subtle motions of stars whipping around its core, revealed a gravitational signature that defied all expectations. The unseen object anchoring those stellar orbits was not a lightweight. It was a supermassive black hole with a mass likely exceeding 1 million times that of our own Sun. To grasp the sheer disproportion of this, imagine discovering a tiny, remote village, and beneath its single town square, finding an engine the size of a nuclear aircraft carrier. The scale is all wrong. This black hole is not just large for its galaxy, it is gargantuan, utterly dominating the feeble gravitational field of its stellar surroundings. Its existence shatters the established scaling law. How did such a titan end up in such a tiny cage? Astronomers are grappling with two profoundly different origin stories, each with dramatic implications. The first theory suggests this black hole is a primordial seed, a relic from the universe's first few 100 million years. In this scenario, it formed directly from the collapse of an immense cloud of primordial gas, a rare and massive first-generation seed black hole. For reasons unknown, the galaxy around it simply failed to grow. Perhaps it was starved of gas by the harsh environment of the cluster, or maybe its growth was stunted by violent interactions with neighbors. The black hole became a king without a kingdom, a giant trapped in an infant's body. The second, more violent theory proposes the opposite sequence of events. What we see today is not the original galaxy, but its stripped remnant. This dwarf galaxy could be the ravaged core of a much larger, more massive galaxy that ventured too close to the cluster's center long ago. In that catastrophic encounter, the outer layers of stars and gas were violently torn away by tidal forces, a process called tidal stripping. The dense central core where the black hole resides would have been the hardest part to disrupt. What remains is essentially the galactic nucleus, the black hole, and a tight swarm of stars that once surrounded it, now adrift as a ghost of its former self. This would mean the black hole's mass is not anomalous at all. It is perfectly normal for the galaxy it used to be. We are simply looking at a cosmic fossil, the skeleton of a devoured giant. This overmassive black hole forces a fundamental question about the history of structure in the universe. Are we looking at a failed giant or the corpse of one? Its presence challenges the narrative of co-evolution, and suggests that the chaotic environment of a dense cluster like Leo can leave behind bizarre relics that rewrite the standard story of galactic life and death. The idea of a giant black hole trapped in a dwarf galaxy forces us to rethink local relationships, but a much closer object is revealing a gravitational pull from far beyond our own neighborhood. Drifting just over 800,000 light-years from Earth is the Leo 1 dwarf spheroidal galaxy, a small satellite of our Milky Way. For decades, it was considered just another member of our local cosmic family, its motion dictated by the gravity of our galaxy and the nearby Andromeda galaxy. Yet when astronomers pinned down its precise trajectory, they found something deeply unsettling. Leo 1 is not behaving like a loyal satellite. Its measured velocity, the combination of its speed toward us and its sideways motion across the sky, shows it is being pulled insistently in a specific direction. It is moving with a peculiar haste toward the distant Leo cluster, millions of light-years away. This is an anomaly that should not exist. The gravitational grip of our local group of galaxies should completely dominate its motion. The immense mass of the Milky Way and Andromeda, locked in their own slow dance, should be the only significant forces on such a nearby dwarf, yet the data is clear. There is an extra component to its velocity, a subtle but undeniable drift that points like a compass needle toward the distant cluster. This suggests a profound and unsettling idea. The gravitational influence of the Leo cluster, or something even more massive behind it, is reaching across the cosmic void to tug on a galaxy right on our doorstep. One potential culprit is a mysterious region of space known as the Great Attractor, a gravitational anomaly located hundreds of millions of light-years away in the direction of the constellations Centaurus and Hydra. This colossal concentration of mass, thought to be a supercluster of galaxies, pulls everything in our galactic neighborhood toward it. Leo 1's anomalous motion could be a tiny part of that vast cosmic river flow. An even more speculative idea points to the phenomenon of dark flow, the suggestion that entire clusters of galaxies are streaming toward a point far beyond the observable horizon, driven by the gravitational pull of structures so immense and distant we cannot see them. If such a flow exists, the Leo cluster itself would be moving, and its gravitational wake could be influencing everything in its path, including our tiny neighbor Leo 1. This makes the dwarf galaxy a critical piece of evidence. It is a local probe, a nearby sensor measuring gravitational forces from the largest scales of the universe. Its anomalous velocity is not just a curiosity about a single small galaxy. It is a clue that the tapestry of gravity weaves together everything, from the satellites of our own Milky Way to the most distant clusters, into a single, interconnected web. The tug felt by Leo 1 hints that the Leo cluster is not an isolated island, but part of a much grander and largely unseen architectural plan. Gravity writes its history not in books but in the torn remnants of its victims. Stretching between the massive galaxies of the Leo cluster, astronomers have mapped faint, shimmering rivers of stars, delicate filaments that trace a path of ancient destruction. They call this particular structure a string of pearls, a tidal stream of staggering length and coherence, and it is the ghostly aftermath of a galactic cannibalism event that concluded billions of years ago. To understand what we are seeing, we must reconstruct the crime. The perpetrator is one of the cluster's dominant elliptical galaxies, a vast, smooth giant whose chaotic core suggests a history of violent mergers. The victim was a smaller dwarf galaxy, perhaps a spiral rich with stars. Billions of years in the past, this smaller galaxy ventured too close. The immense differential gravity of the giant galaxy did not strike it like a hammer, but pulled it apart like taffy. Think of it as a cosmic tide, stretching the dwarf galaxy first into a long, thin strand of stars and gas, and then wrapping that strand around the predator in a vast, looping orbit. Over eons, the stars within that strand have spread out along their path, but they have not scattered randomly. they remain gravitationally connected, tracing the precise orbital highway of their progenitor. This is the string of pearls we see today. Each faint clump of light along the stream is not a coincidence, but a telltale sign of the dwarf galaxy's original structure. These are the pearl-like overdensities, regions where stars from the victim's core or its star clusters were more tightly bound and resisted being completely smoothed out. By meticulously measuring the brightness, color, and motion of these stellar pearls, astronomers can perform a kind of celestial forensics. The color of the stars tells their age and composition, revealing what the original dwarf galaxy was made of. The stream's curvature and the speed of stars within it allow scientists to rewind the orbital clock, calculating not only when the cannibalism began, but also the mass of the giant galaxy that did the consuming. This turns the stream into a dynamic scale, weighing the invisible dark matter halo of the predator galaxy by observing how it bent the path of its prey. This single, elegant strand is therefore a multi-billion-year-old fossil record. It confirms that the serene, featureless appearance of giant elliptical galaxies is a mask hiding a violent past of consumption and growth. The Leo cluster, in its present form, was built through such acts of galactic predation. Every faint stream we can detect is a chapter in that construction history, a silent witness to the hierarchical merging that shaped the cosmos. The persistence of these structures is itself a mystery, as the chaotic gravitational environment of the cluster should have stirred and dissolved them long ago. Their survival suggests these mergers happened in a quieter epoch, or that the streams are on a peculiarly stable path, a final orbit forever memorializing a long-finished feast. But the history of violence in the Leo cluster is not written only in stars. It is also etched into the very fabric of space between the galaxies, in a medium so thin it is almost a perfect vacuum, yet hot enough to glow in X-rays. This is the intracluster medium, a superheated soup of plasma, and within it, astronomers have found ghostly imprints. These are the fossil radio bubbles, colossal cavities that can span hundreds of thousands of light years, visible only as faint whispers to radio telescopes. They are not active explosions, but the lingering scars of them. To find one, you must look for an absence. In the brilliant X-ray glow of the hot intracluster gas, these bubbles appear as vast, dark voids, regions where the multimillion-degree plasma has been pushed aside, creating a pocket of much cooler, less dense material. But the bubbles themselves are not empty. They are filled with a sea of extremely energetic particles and magnetic fields, which emit a faint, diffuse radio signal, a signature that can persist long after the event that created them has ceased. Think of it like a balloon submerged in water. The water is the hot, X-ray emitting plasma. The balloon is the bubble, and its rubber skin is a shell of magnetized particles. Even after you stop blowing air into the balloon, its shape remains, displacing the water for a remarkably long time. That is precisely what these fossil bubbles are, balloons of cosmic energy inflated billions of years ago that have not yet popped or dissolved. Their immense size points to a truly monstrous engine, a supermassive black hole in the core of a dominant cluster galaxy that once went through a period of ferocious activity. During these active phases, black holes do not just consume matter, they can also fire out titanic jets of plasma and energy at nearly the speed of light from their poles. These jets plow into the surrounding intracluster medium, inflating these gigantic cavities and pushing the hot gas aside. Eventually, the black hole's activity subsides, the jets turn off, and the brilliant beacon of a quasar fades. But the bubble remains, buoyantly floating upward through the cluster atmosphere like a bubble in a glass of champagne, its radio glow slowly fading over hundreds of millions of years. The discovery of multiple such fossil bubbles in Leo is therefore a form of cosmic archaeology. Each one is a timestamp, a record of a cataclysmic outburst that happened in the deep past. By mapping their positions and sizes, astronomers can reconstruct a timeline of violent activity in the cluster's heart. It reveals that the central black holes have not been quiet landlords but episodic tyrants, erupting in fits of incredible energy that reshape their entire environment. These ghosts of past explosions do more than just mark history, they actively shape the present. By displacing the hot gas, they regulate the flow of material onto the very galaxies that host the black holes, potentially stifling star formation and influencing the growth of the cluster itself. They are the fossilized breaths of sleeping giants, and their silent presence is a reminder that the calm we see today in the Leo cluster is merely a pause between titanic, history-altering events. That history of violent outbursts has left a permanent mark on the cluster's very anatomy. Most giant galaxy clusters settle into a predictable structure as they age, developing a calm, dense heart. In this so-called cool core, the superheated gas between galaxies has had time to relax, pool together, and gradually cool down, sometimes enough to condense into new stars. It is the cluster equivalent of a placid, deep lake. The Leo cluster, however, presents a radically different picture. X-ray telescopes reveal its core not as a serene pool, but as a churning, turbulent sea. The hot gas is sloshing. It shows a distorted, asymmetrical shape with ripples and edges that look stirred and disrupted. This is the signature of a system without a stable, cool core, a cluster whose heart was violently stirred too recently to have settled back down. The cause of this disturbance points to a cataclysm of almost unimaginable scale. The sloshing motion we see is not random turbulence. It is a specific, coherent pattern like water in a giant bowl that has been sharply bumped. That bump was almost certainly a recent, colossal merger. Sometime in the last 1 or 2 billion years, a substantial subgroup of galaxies, perhaps an entire smaller cluster, came plowing into the heart of the Leo cluster at millions of miles per hour. This was not a gentle blending. It was a head-on collision between two immense gravitational ecosystems. As the incoming group fell through the main cluster, its own dark matter halo and galaxies would have acted like a cosmic paddle, violently stirring the hot gas in the core, disrupting its calm and mixing the different temperature layers together. This event would have prevented the gas from cooling and pooling, effectively destroying any pre-existing cool core and leaving behind the chaotic, stirred-up state we observe today. This missing cool core is therefore more than just an oddity, it is a cosmic clock. By studying the size and nature of the sloshing motions in the X-ray gas, astronomers can perform a form of forensic timing. They can model how long it would take for such ripples to gradually smooth out and dissipate under the cluster's own gravity. The fact that we still see such clear, sharp disturbances tells us the merger was a relatively recent event in cosmic terms, likely occurring within the last 1 to 2 billion years. This gives us a precise chapter in the cluster's biography. It tells us that the Leo cluster we see today is not a finished, relaxed structure. It is a system still recovering from the single most violent episode in its recent history, an event that reshaped its internal landscape on a scale spanning millions of light years. This understanding transforms our view of clusters from static cities of galaxies into dynamic, evolving entities, where the most dramatic changes come from these rare, universe-shaking collisions. This sloshing, chaotic core is the perfect stage for a cosmic catapult. Within the turbulent heart of the Leo cluster, astronomers have spotted galaxies moving with impossible speed, racing on trajectories that seem destined for exile. These are high-velocity galaxy ejecta, celestial bodies flung outward with such force they could break free from the cluster's immense gravitational pull entirely. One such galaxy, a fast-moving dwarf or perhaps a stripped spiral, serves as our case study. Its measured velocity is not just high, it is extreme, far exceeding the typical orbital speeds of its neighbors. To achieve such a launch requires a gravitational event of breathtaking precision and power. The leading explanation is a three-body interaction, a celestial game of billiards played with entire galaxies. Imagine a smaller galaxy passing too close to a tight binary pair of massive galaxies orbiting each other. In a complex gravitational dance, the interloper can steal a tiny fraction of the binary system's immense orbital energy. The result is a slingshot effect. The binary pair, now slightly more tightly bound, serves as the anchor, while the third galaxy is flung away at a tremendous velocity, like a stone from a giant's catapult. Another possibility ties directly to the cluster's violent history. During the colossal merger that stirred the core, the chaotic gravitational fields could have acted as a vast, uneven accelerator. A galaxy passing through just the right region at just the right time could have received a series of gravitational kicks, each one adding speed, ultimately booting it toward the cluster's outskirts at an escape velocity. This phenomenon forces us to look beyond the cluster's borders into the immense, empty voids between such structures. Drifting in those lonely expanses are so-called field galaxies, isolated islands of stars with no cluster to call home. Their origin has long been a puzzle. The high-velocity ejecta in Leo provide a compelling answer. These rogue galaxies may not have formed in solitude. They could be refugees violently expelled from their crowded birth clusters billions of years ago in similar slingshot events. They are the cosmic runaways cast out by the very gravitational machinery that built their homes, now condemned to wander the eternal dark between the lights of the universe. That same violence which ejects galaxies also leaves behind a more subtle, haunting signature. A faint, omnipresent glow permeates the dark spaces between the brilliant galaxies of the cluster. This is not the hot, X-ray emission of gas, but the collective, ancient starlight of countless suns that no longer belong to any galaxy. Astronomers call it intracluster light, and in the Leo cluster, its sheer abundance presents a profound paradox. This ghostly luminescence comes from stars that were violently liberated. During the mergers, collisions, and tidal disruptions that built the cluster, individual stars were stripped from the outer fringes of their home galaxies and flung into the intergalactic void. These orphan stars, mostly old, red, and faint, now wander forever in the immense gravitational field of the cluster itself, forming a diffuse cosmic fog. The amount of this light is a direct fossil record of past violence. More interactions mean more stripped stars, which means a brighter intracluster glow. The problem is, when scientists compare the actual observed glow in Leo to sophisticated computer simulations of how such a cluster should form, the numbers do not match. The real cluster shines with significantly more of this ghost light than the virtual one. There is simply too much of it. This excess is a glaring clue that our simulations, our best models of cosmic evolution, may be missing a key ingredient of chaos. It suggests the history of the Leo cluster has been even more tumultuous, more filled with frequent and violent close encounters than we have dared to imagine. Perhaps the giant elliptical galaxies at the cluster's heart underwent more numerous smaller mergers in their past, each one shedding a spray of stars into the void rather than a few catastrophic collisions. Or maybe the process of tidal stripping is far more efficient than our physics codes can currently replicate, peeling stars away from galaxies with a gentle, relentless persistence that adds up over billions of years. This faint glow forces us to rewrite the cluster's biography in light. Every extra photon of intracluster light is a witness to a forgotten act of galactic dismemberment. It means the serene giants we see today are not just the products of a handful of major mergers, but of a continuous, brutal ballet of destruction that has been scattering stars into the darkness for eons. The very emptiness between galaxies is not empty at all. It is a museum of exile, illuminated by the accumulated sorrow of a billion stellar refugees. This ghostly sea of exiled stars is not the only unseen light haunting the cluster. In a different part of the spectrum, a brilliant but invisible beacon shines. Data from space telescopes like Spitzer and WISE have pinpointed a powerful, mysterious source of infrared light in the Leo cluster, a source with no clear optical counterpart. To our eyes and to telescopes that see visible light, this region of space appears dark and unremarkable. But in the infrared, it blazes like a cosmic furnace, a radiant heat signature with no obvious face. This is the challenge of the unidentified infrared emitter, a puzzle where the most important clue is what we cannot see. Infrared light is the signature of warmth, of objects too cool to glow in visible light but still radiating heat. A strong, isolated source like this typically points to one of two cosmic powerhouses, but both are usually visible. The first candidate is a starburst galaxy, a galaxy undergoing a frenzy of star formation so intense it is literally burying itself alive. In such a place, thousands of massive stars are born in dense clouds of gas and dust. These stars live short, violent lives, and their intense ultraviolet radiation is absorbed by the thick, surrounding cocoons of cosmic dust. The dust heats up to temperatures of tens or hundreds of degrees and re-radiates that absorbed energy not as visible light, but as a torrent of infrared. The galaxy's own brilliant stellar nurseries are completely hidden behind this self-made veil of soot, visible only as a warm, diffuse glow from the outside. The second prime suspect is a hidden quasar. Imagine a supermassive black hole in the core of a galaxy, feeding ravenously on matter. As material spirals in, it forms a brilliant, hot accretion disk that can outshine its entire host galaxy. But if that core is surrounded by a thick, donut-shaped ring of dust and gas, that dazzling optical and ultraviolet light is blocked. Just like with the starburst, the dust absorbs the fierce energy, heats up, and re-emits it in the infrared. From our vantage point, we would see only the warm, dusty donut, not the brilliant engine inside. Yet the mystery deepens because this source is so isolated and intense that it resists even these exotic explanations. Could it be something far rarer? Some astronomers dare to speculate about a relic from the dawn of time, a cluster of population 3 stars. These would be the universe's very first stars, hypothetical giants hundreds of times more massive than our Sun, composed only of hydrogen and helium. They would have burned ferociously and died young, and their light would be heavily redshifted and possibly obscured by primordial dust. Finding such a cluster would be like discovering a living dinosaur, a direct window into the first chapter of star formation. While unlikely, the possibility lingers because our current telescopes simply cannot peer through the obscuration to see the source's true nature. This is why this unseen emitter is a top priority for the James Webb Space Telescope. Webb is an infrared machine designed to see the heat of the cosmos with unprecedented clarity and resolution. Its mission here is to act as a cosmic pathologist, performing a spectral autopsy on this infrared glow. By breaking the light into its component colors, Webb can search for the specific chemical fingerprints, the telltale lines of oxygen, hydrogen, or carbon that would reveal what is powering the emission. It could resolve whether the light comes from a compact point, like a hidden quasar, or a more extended region, like a shrouded galaxy. This unidentified source represents the frontier of the unknown, a glaring signal in our data that belongs to an object we cannot classify. It proves that even in an age of magnificent telescopes, the universe can still hide its most brilliant fires behind the thinnest of cosmic curtains. The universe's hidden architecture may be written in the very spin of galaxies. A curious, large-scale pattern emerges when astronomers map the orientations of spiral galaxies within the Leo cluster. Many of these majestic pinwheels appear to have their axes of rotation aligned with each other, and perhaps even with the invisible filamentary structure of the cluster itself. This is not what you would expect from random chance. In a chaotic cosmos, galaxies should spin in every possible direction, like tops scattered randomly on a floor. Yet here, there is a whisper of order, a subtle coordination on a scale of millions of light years. This phenomenon, called spin alignment, presents a profound choice between two origins, each reaching back to a different epoch in time. The first theory looks to the very beginning. Galaxies form from the collapse of immense clouds of gas within the cosmic web, the vast network of dark matter filaments that stretches across the universe. If the primordial gas in these filaments already had a preferred direction of motion, a kind of cosmic swirl imprinted by the universe's earliest moments, then the galaxies that condensed from it might inherit that spin orientation. Their alignment would be a fossil, a preserved memory of the conditions in the infant cosmos carried forward for over 13 billion years. The alternative theory is about influence, not inheritance. It suggests the cluster itself, over eons, has forced these galaxies into line. As a spiral galaxy falls into the dense gravitational well of the cluster, it experiences immense tidal forces. Think of it as a vast, gentle hand gripping the galaxy and slowly, patiently twisting it. The differential pull of the cluster's gravity can torque the galaxy, altering its spin axis over billions of years to align with the overall flow of material into the cluster or with the shape of the cluster's own dark matter halo. This would be a story of cosmic conformity, where the environment gradually erases individuality. Distinguishing between these two possibilities is incredibly difficult because they predict a similar outcome. The key may lie in the galaxy's ages and locations. Are the aligned galaxies primarily older ones that have been in the cluster for a long time, their spins potentially reshaped by its tides? Or are they also found on the outskirts, newly arrived systems that might still carry their primordial imprint? Each observed galaxy is like a single compass needle. The question is whether they all point in the same direction because they were manufactured that way, or because a powerful magnetic field has slowly swung them into agreement. This subtle clue, written in the silent rotation of stars and gas, connects the largest structures we see today to the very first moments of everything. It asks whether the universe's initial spin has echoed down through time, or if gravity alone can write such elegant order into the chaos of a cluster. The subtle alignment of galactic spins hints at a deep cosmic order, but when we count the smallest members of the cluster, that order seems to break down entirely. Our most sophisticated supercomputer simulations of the universe paint a very specific picture of cosmic structure. They tell us that a massive gravitational nexus like the Leo cluster should be absolutely swarming with thousands of tiny dwarf galaxies, the smallest galactic building blocks, held in its vast dark matter halo like a cloud of gnats around a street lamp. Yet when astronomers point their telescopes at Leo, they do not see that predicted swarm. They see only a few hundred at most. This glaring mismatch is known as the missing satellites problem, and in the dense environment of Leo, it becomes a critical test of our entire understanding of how the cosmos builds itself from the ground up. Where did all those dwarfs go? The first and most straightforward answer is that we simply cannot see them. Our telescopes, even the most powerful ones, have limits. A dwarf galaxy with very few stars, or one that is composed almost entirely of dark matter, would be incredibly faint, a ghostly smudge lost in the glare of its giant neighbors or the background glow of the sky. It is possible the Leo cluster is filled with these ultra-faint, dark matter-dominated ghosts, and we have only begun to scratch the surface of finding them. Every new, deeper survey of the cluster has the potential to uncover more of these hidden dwarfs, slowly closing the gap between prediction and observation. The second possibility is far more destructive. The Leo cluster is a violent gravitational arena. Perhaps the missing dwarfs were not just born dark, but were literally torn apart. A tiny dwarf galaxy venturing too close to a giant elliptical galaxy, or passing through the dense, turbulent core of the cluster, would be subjected to devastating tidal forces. These forces could strip the dwarf of its already meager stars and gas, dissolving it into the faint intracluster light, or simply dispersing its material beyond recognition. In this scenario, the cluster is not missing its dwarfs, it has already digested them. The relative scarcity we see today would be the result of billions of years of cosmic carnage, leaving behind only the hardiest or most distant of these small galaxies. But the most profound solution challenges the very foundation of the simulations themselves. These virtual universes run on our best current models of dark matter, known as cold dark matter. In this model, dark matter particles move slowly and clump together easily, leading to a universe that is very lumpy on small scales, producing a plethora of dark matter halos ready to host dwarf galaxies. The mismatch in Leo could be a sign that dark matter behaves differently than we think. Perhaps it is slightly warm, meaning the particles move faster, preventing the formation of as many tiny clumps. Or perhaps complex physics involving stars and supernova in the early universe blew out the gas from these small halos, preventing stars from ever forming within them, leaving behind legions of completely dark, invisible halos. The too many dwarf problem forces a humbling realization. Either our observational tools are still too weak, our understanding of the violent cluster environment is incomplete, or the nature of dark matter itself is not as simple as our most elegant theories suppose. The quiet emptiness around the Leo cluster, then, is not empty at all. It is either a graveyard, a hiding place, or a message written in missing light, telling us that the smallest scales of the cosmos hold the keys to its largest mysteries. This quiet emptiness is shattered by a single, brilliant millisecond. From the general direction of the Leo cluster's outskirts, a telescope on Earth once caught a fleeting scream of radio energy, a signal so powerful it outshone entire galaxies. This was a fast radio burst, a mysterious pulse of cosmic static that appeared and vanished in less time than it takes to blink, and its possible link to Leo adds a thrilling new layer to the cluster's catalogue of enigmas. To understand why this detection, even if tentative, sends such a shockwave through astronomy, you have to grasp what a fast radio burst truly is. Imagine all the radio energy our sun emits over an entire day, compressed and fired into the universe in a single, blazing thousandth of a second. That is the raw, staggering power of an FRB. For that brief instant, it becomes the brightest radio source in its entire region of the sky, a cosmic flashbulb popping in the dark. The mystery is not just its power, but its source. Most FRBs detected are one-off events. They flash once from a point in the sky and are never heard from again. This makes them nearly impossible to pin down. They are like a single, deafening gunshot echoing across a mountain range. You hear it clearly, but pinpointing the exact canyon it came from before the echo fades is a monumental challenge. The frantic search begins the moment the burst is detected. The first crucial clue is its dispersion. As the radio waves travel across millions of light years of intergalactic space, they pass through traces of ionized gas. This gas acts like a cosmic filter, slowing down lower-frequency radio waves more than higher-frequency ones. By measuring how much the burst signal has been spread out or dispersed, astronomers can estimate the total amount of material it has traveled through, giving them a rough distance. The burst from Leo's direction carried the signature of a long journey, placing its origin far beyond our own galaxy, deep in the cosmic realm where clusters like Leo reside. But a direction and a distance are not enough. The volume of space that encompasses the Leo cluster is immense. To solve the crime, astronomers needed to find the host galaxy. They scrambled to point the world's most powerful optical, infrared, and X-ray telescopes at the region, searching for any telltale sign, any afterglow or peculiar galaxy that could be the culprit. Did the burst come from one of the giant ellipticals, perhaps linked to activity around its central black hole? Or from a star-forming dwarf, the kind of turbulent environment that might breed such explosions? Or perhaps from a completely dark, unidentified galaxy floating in the cluster's halo? Without a repeat performance or a precise location, the search remains open, a cold case written in radio waves, This uncertainty is what fuels the wild spectrum of theories. On the more natural end, the prime suspect is a magnetar, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from halfway across the solar system. A starquake on such a monstrous object, a sudden cracking of its crust under magnetic strain, could theoretically release the colossal energy of an FRB. Other ideas involve cataclysmic finales, like the collision of two ultra-dense neutron stars or the evaporation of a black hole. And then, of course, there is the speculative frontier. Could such a focused, energetic burst be a beacon, a side effect of unimaginably powerful alien technology, like a light sail being pushed by a planetary-scale radio transmitter? While considered highly unlikely by most scientists, the idea persists because, for now, no natural explanation is fully proven. A confirmed FRB from within the Leo cluster would be a game-changer. It would place this mysterious phenomenon squarely inside a dense, well-studied environment, giving astronomers a rich context they desperately lack. They could examine the host galaxy's age, its star formation rate, its history of violence, searching for the common conditions that might breed these brilliant flashes. Is there something specific about the crowded, turbulent environment of a cluster that triggers them? The single, unconfirmed millisecond from Leo's direction is a tantalizing hint that the cluster's mysteries are not just written in light and gravity, but also in sudden, deafening bursts of static waiting to be decoded. That fleeting burst of radio energy hints at sudden violence, but the cluster's hot atmosphere tells a story of slower, more immense forces. X-ray telescopes reveal a startling feature etched into the multimillion-degree gas, sharp, razor-thin edges that slice through the glowing plasma. Astronomers call these structures cold fronts, and their name is a cosmic misdirection. They are not actually cold. In the searing heart of the cluster, a cold front might still be 10 million degrees Celsius. The cold is only relative to the even hotter gas around it, perhaps 20 or 30 million degrees. What defines these fronts is not temperature alone, but a dramatic discontinuity in density and pressure. Picture a weather front on Earth where a mass of cool, dense air butts up against a region of warm, less dense air, creating a sharp boundary in the sky. The physics here is strikingly similar, but played out on a scale where the air is a superheated plasma and the front can stretch for 500,000 light-years. These are the weather maps of intergalactic space. Their formation is a direct result of motion within the cluster. Imagine a massive galaxy or an entire subgroup of galaxies moving steadily through the intracluster medium. It does not crash through like a bullet, but plows through like a ship through water at subsonic speeds. This motion creates a cosmic slipstream. The gas in front of the moving object gets piled up and compressed, forming a dense, slightly cooler layer. Behind it, a turbulent wake of eddies and swirls may form. The sharp boundary between this accumulated, denser gas and the undisturbed, hotter gas of the cluster is the cold front we observe. It is a standing wave of plasma frozen in the X-ray glow. By meticulously mapping the shape, curvature, and sharpness of these fronts, astronomers can read them like a history book. The front's smoothness tells us about the gentleness of the motion, a lack of violent turbulence that would have shredded the boundary. Its curvature can reveal the shape and orientation of the object that created it, like the bow wave of a ship. Most importantly, by comparing the position of the front to the galaxy that likely made it, scientists can measure how far the galaxy has traveled since the front formed, essentially creating a clock. This allows them to reconstruct the dynamics of the cluster not as a static snapshot, but as a dynamic movie unfolding over hundreds of millions of years. These immense, delicate structures prove that the space between galaxies is not a uniform soup, but a fluid sculpted by the slow, majestic passage of its largest inhabitants, a dance of gravity and plasma where every movement leaves a permanent scar in the heat of the void. Gravity's lens is supposed to be a predictable instrument. The immense mass of the Leo cluster warps the fabric of space-time, bending the light from galaxies far behind it into stretched arcs and multiple mirrored images. Astronomers use this effect called strong gravitational lensing like a cosmic scale, weighing the cluster's total mass by measuring how severely it distorts the background sky. But in one particular case, the lens has produced a surprise. A single, distant galaxy lensed into a faint arc appears just a little too bright, its image slightly too magnified compared to what the best mass models of the cluster predict. This tiny discrepancy is a glaring clue, a single bent photon out of place in a cosmic crime scene. The models account for all the visible galaxies and the smooth, enormous halo of dark matter enveloping the entire cluster. Yet something is missing. The extra magnification suggests an extra knot of gravity along our line of sight, a hidden mass compact enough to further twist the light. The prime suspect is a dark matter subhalo, a dense clump of pure dark matter that never managed to attract stars or gas, floating invisibly within the cluster's vast halo. Its presence would be a stunning confirmation of the cold dark matter model, which predicts thousands of such unseen clumps. Finding one directly by the shadow it casts with gravity alone would be a monumental first. But the evidence is circumstantial. The anomaly could point to something else entirely, a flaw in our assumptions about the lens itself. Perhaps the distribution of the hot, X-ray emitting gas, which contributes significant mass, is more lumpy and complex than we've mapped. Or maybe the visible galaxies themselves have more extended, unseen stellar halos than we've accounted for, adding subtle, local bumps to the gravitational landscape. This lensing anomaly is a classic detective story where every suspect is invisible. Is it a dark matter ghost finally revealing itself by its gravitational fingerprint? Or is it a sign that the visible universe is more intricate, its mass woven together in ways our smooth models oversimplify? The bent light holds the answer, but for now, it only deepens the mystery of what precisely is hiding in the dark. That bent light points to hidden knots of gravity, but a brilliant beacon on the cluster's fringe reveals a different kind of hidden history. The light from a distant quasar, a supermassive black hole shining with the heat of a devoured galaxy, carries a peculiar chemical signature in its spectrum. When astronomers dissected that light, they found the clear fingerprints of heavy elements oxygen, carbon, iron, in the vast clouds of gas swirling around the cosmic engine. This is the quasar with unusually metal-rich gas, and its location makes this finding profoundly strange. Heavy elements, which astronomers call metals, are not born in the Big Bang. They are forged in the nuclear furnaces of stars and scattered across space by stellar winds and supernova explosions. Finding metal-rich gas around a quasar means that region of space has witnessed generations of stars living and dying, polluting the primordial hydrogen with the ash of their creation. It speaks of a long, fertile history of star formation. The mystery is that this quasar does not appear to sit in a bustling galactic metropolis. It lies in a relatively isolated region on the outskirts of the Leo cluster, a place where we might expect to find more pristine, unprocessed material, not this chemically mature environment. How did this pocket of space become so enriched? One compelling theory looks to a dramatic past. The quasar's host galaxy may not be the isolated dwarf it appears to be today. It could be the ravaged core of a once massive spiral galaxy that ventured too close to the cluster's heart billions of years ago. In that catastrophic encounter, the outer arms of stars and gas were violently stripped away by tidal forces, flung into the intracluster medium to become part of that ghostly light. What remained was the galactic nucleus, the central black hole, and the dense, metal-rich gas that had already been polluted by eons of star formation in the original galaxy's core. This would make the quasar we see a survivor, a brilliant tip of a galactic iceberg with the rest of its mass hidden as faint streams or completely dissolved. The metal-rich gas is the forensic evidence of that lost grandeur. The other possibility is that this region was not always so quiet. The quasar could be the aftermath of a major merger between two gas-rich galaxies that occurred right where it sits. That collision would have triggered a ferocious burst of star formation, a starburst that quickly seeded the surrounding gas with heavy elements before the central black hole awoke into its brilliant quasar phase. The merger remnants could have since dispersed or faded, leaving the quasar shining alone, a lighthouse standing on the eroded ruins of a cosmic shipwreck. This single point of light forces a question about the cluster's history. Is the periphery actually littered with these galactic ghosts, the stripped nuclei of ancient giants? It suggests that the violent processes we see shaping the cluster's core also extend their influence far into its outskirts, leaving behind brilliant, chemically rich tombstones to mark the passing of entire galaxies. The quasar's light is not just a beacon of consumption, but a message in a bottle, telling the story of a lost world we can no longer see. A different kind of ghost haunts the cluster's outer fields, one seen not by its absence of light, but by the silent radio whisper of its hydrogen. Deep radio surveys have mapped a distinct, rotating cloud of neutral hydrogen gas, designated as an HI region, that possesses all the coherent motion of a spiral galaxy. This vast reservoir of cold gas spins with a graceful, organized velocity, tracing a classic rotation curve. Yet, when astronomers point every optical and infrared telescope they have at that precise location, they find nothing. No smudge of stars, no glow of stellar nurseries, not even the faintest collection of ancient suns. It is a galaxy's signature without the galaxy, a cosmic dance with no visible dancers. This is a premier candidate for a dark galaxy, a body potentially composed almost entirely of primordial gas and the gravitational anchor of dark matter. The technique that revealed it is a marvel of indirect observation. Radio telescopes tune into the specific frequency emitted when the single electron in a neutral hydrogen atom flips its spin, a tiny quantum jump that creates a signature 21-centimeter line. By measuring the Doppler shift of this line across different parts of the cloud, astronomers can chart the gas's motion. What they found was a smooth, rising rotation curve. The gas on the outer edges moves just as fast as the gas near the center. This is the classic telltale sign of dark matter. In a system held together only by the gravity of the visible gas, the outer material should orbit more slowly. The fact that it does not mean a massive, unseen halo must be present, providing the extra gravitational glue to whip that outer hydrogen around. The hunt then turned to find any stars at all. Teams have used the deepest, most sensitive optical surveys, staring for hours to collect every possible photon. They have searched for the subtle, extended glow of old, red stars that might be too diffused to see as individual points. They have looked for the infrared warmth of any hidden stellar nurseries. So far, the result is a profound and puzzling silence. If even a handful of stars existed, we should see them. Their absence is what makes this object so revolutionary. Could this be a primordial building block frozen in time? A clump of gas and dark matter from the early universe that, through some quirk of its environment in the cluster, never triggered the collapse and ignition of star formation. It would be a living fossil of the cosmic dark ages, a preserved blueprint for a galaxy that never was. Alternatively, it might represent a new class of object altogether, a stable structure where the conditions for star formation are perpetually suppressed, perhaps by the gentle but persistent pressure of the surrounding intracluster medium or by a lack of the initial seed needed to begin the collapse. Its existence challenges the very definition of a galaxy. Must a galaxy have stars, or is it enough to have the coherent structure, the identity, granted by a rotating disk of gas bound by gravity? A confirmed dark galaxy would force us to rewrite the narrative of structure formation, suggesting that for every brilliant spiral like our Milky Way, there could be countless dark siblings, invisible skeletons of gas and shadow that never lit their candles, silently orbiting in the darkness between the stars. That silent, rotating cloud of hydrogen gas is not the only invisible force shaping this cosmic arena. Spanning the entire breadth of the Leo cluster, from its churning core to its outermost fringes, is a vast and organized magnetic field. We cannot see it directly, but we can read its signature in the light that passes through. When radio waves from distant quasars and galaxies travel through the cluster, the field subtly twists them, aligning their waves in a specific direction, a property astronomers call polarization. By mapping this polarization across the sky, scientists have traced the outline of a magnetic structure of almost unimaginable scale, one that coheres across millions of light years. Its very existence presents a monumental puzzle. How do you build and maintain a magnetic field the size of a galaxy cluster? Magnetism on Earth is simple by comparison. Our planet's field is generated by the churning of molten iron in its core. A star's magnetic field arises from the turbulent motion of plasma in its interior. But a galaxy cluster is mostly empty space, a near-perfect vacuum filled with a super-thin, super-hot plasma. There is no solid core to spin, no defined surface to churn. So where did this immense field come from, and what keeps it from simply fading away into the void? The theories take us back to the very beginning. One profound idea suggests the field is primordial. In the universe's first fractions of a second during the period of cosmic inflation, quantum fluctuations could have sown the seeds of magnetic fields on microscopic scales. As the universe expanded exponentially, these tiny magnetic seeds would have been stretched to cosmological sizes, woven into the fabric of space-time itself. Later, as galaxies and clusters formed, these weak, primordial fields would have been pulled along with the collapsing gas, compressed and amplified by the chaotic motions until they reached the strengths we detect today. In this story, the field in Leo is a fossil, a whisper from the first moments of everything, amplified by time and gravity. The competing theory is one of bottom-up construction, a slow, relentless accumulation of chaos. Imagine the cluster not as a blank slate, but as a canvas that has been spray-painted by countless cosmic events over billions of years. Every supernova explosion in every member galaxy does not just blast out heavy elements, it also injects a torrent of magnetized plasma into intergalactic space. Every outburst from an active galactic nucleus, every jet from a central black hole, is a fire hose of magnetized energy that plows into the intracluster medium. Individually, these events are messy and disordered, their magnetic fields pointing in random directions, but over cosmic time, as these injections mix and stretch through the gentle, large-scale motions of the cluster's gas, something remarkable happens. The turbulent motions can actually organize the chaos, shearing and folding the magnetic field lines until they align on vast scales, much like kneading dough eventually aligns the gluten strands. The field we see today would be the sum of 1 billion stellar deaths and 1 million black hole eruptions, smoothed and ordered by the patient flow of the cluster's atmosphere. This invisible architecture is far more than a cosmic curiosity. It is a fundamental component of the cluster's ecosystem, a force that shapes behavior from the smallest particles to the largest gas clouds. This magnetic field acts as a cage and a conduit for the sea of high-energy particles that also fills the cluster. It traps cosmic rays, preventing them from escaping too easily, and guides them along its lines like trains on a track. This is crucial for creating the faint, diffuse radio glow of the fossil bubbles we discussed earlier. The field also influences how the hot gas itself behaves. It can provide a kind of microscopic scaffolding, adding tension and pressure that affects how the gas sloshes, how it mixes, and how it resists being compressed. It may even play a role in stifling the formation of new stars in certain regions by providing extra support to gas clouds, preventing them from collapsing under their own weight. So, is the magnetic field of the Leo cluster a relic of creation or a product of its own violent history? The answer may be both. A weak seed from the early universe could have provided the initial thread, which was then dramatically embroidered by the life and death of countless stars and black holes. This invisible matrix reminds us that the cosmos is not just shaped by gravity and light. It is also a magnetic universe where forces we cannot see weave order into the chaos, governing the flow of energy and the fate of matter across the deepest voids. This vast, silent field is the final entry in our catalogue, a testament to the hidden layers of complexity that govern even the grandest structures we can observe. This vast magnetic field is far more than a silent scaffold. It is an active prison for the universe's most energetic particles. Trapped within its invisible lines are countless cosmic rays, atomic nuclei stripped of their electrons and accelerated to velocities just a whisper below the speed of light. These particles are the shrapnel of cosmic violence, born in the shock waves of supernova explosions or the relativistic jets of supermassive black holes. Once ejected, they would normally streak unimpeded across the cosmic voids, but within the Leo cluster, they encounter the immense tangled web of magnetism. The field acts as a perfect magnetic bottle. As a charged cosmic ray tries to cross the magnetic field lines, it does not travel in a straight line. Instead, it gets caught, forced to spiral tightly around a single line like a bead on a wire. When it tries to escape, the field bends its path, reflecting it back inward. This process happens again and again, trapping the particle in a chaotic, bouncing dance that can last for millions of years. The entire cluster becomes a colossal reservoir, a storage tank brimming with unimaginable energy. This trapped energy does not sit idle. It constantly interacts with its surroundings, solving two major puzzles at once. The first involves a faint, pervasive glow. Astronomers have long detected a diffuse haze of gamma rays, the most energetic form of light, emanating from some galaxy clusters. The source was mysterious. We now understand that this glow is the direct signature of the imprisoned cosmic rays. When these high-speed particles collide with the slow-moving protons of the hot intracluster gas, or with the photons of the ancient cosmic microwave background radiation, the impacts are so violent they generate gamma rays. The magnetic field, by confining the cosmic rays for eons, ensures these collisions happen frequently enough to produce the faint, galaxy-wide glow we can detect. It turns the entire cluster into a faintly shimmering lantern of the highest energy physics. The second puzzle is thermal, concerning the heat of the cluster itself. The intracluster gas is searingly hot, and for it to remain that way for billions of years, there must be a source of energy input to balance the constant loss of heat through X-ray emission. The reservoir of cosmic rays provides a crucial part of that balance. These trapped particles do not just create light, they also stir the pot. Their relentless motion and interactions help to reheat the plasma, injecting turbulence and preventing it from cooling too quickly and collapsing into a runaway cascade of star formation. This means the magnetic field, through its role as a cosmic jailer, directly regulates the cluster's life cycle. It governs whether giant elliptical galaxies at the heart of the cluster remain red and dead or experience unexpected late-life bursts of stellar birth. The field is not a passive ornament, it is a fundamental part of the cluster's circulatory system, a key player in a grand cosmic ecology where gravity, light, and magnetism are in constant dynamic conversation. If the field is truly primordial, it means we are touching a force born in the first trillionth of a second of everything. This hypothesis dares to suggest that the magnetic scaffold spanning the Leo cluster is not a product of its violent history, but a whisper from the cosmic dawn, stretched and amplified to a scale we can finally detect. The idea hinges on a sequence of events that feels almost mythical. In the unimaginable energy of the universe's first moments during the epoch of inflation, quantum fluctuations could have created minuscule magnetic fields, weaker than those on a refrigerator magnet, woven into the fabric of spacetime itself. As the universe expanded at a rate faster than light, these embryonic fields were stretched across cosmic distances, becoming incredibly vast but immeasurably faint. They would have been a ubiquitous background hum, a fundamental texture of the newborn cosmos. Later, as gravity began to pull matter together to form the first galaxies and clusters, this weak, all-pervading field would have been pulled along with the collapsing gas. The simple act of compression, of squeezing this magnetic whisper into a smaller volume, would have intensified it. Further amplification would come from the turbulent motions of the gas during the cluster's violent formation, like stirring a cup of coffee magnifies the swirls. In this story, the field we measure today is a fossil, a direct imprint from a time before stars, before atoms, even before light could travel freely. The evidence for this is subtle but compelling. The field's coherence across such a vast, unstructured volume is difficult to explain if it were built solely from the messy, localized injections of supernova and black hole jets. Those events tend to create patchy, disordered magnetism. The observed large-scale order, especially in the cluster's quieter outskirts, better matches the smooth, stretched signature of a primordial origin. Furthermore, some models suggest that the specific strength and structure of the field in relaxed clusters like Leo align more closely with predictions from primordial amplification than from astrophysical sources alone. Yet the hypothesis is fiercely contested. Critics point to an enormous obstacle, the dynamo effect. Within galaxies, we know that turbulent motions can take a weak seed field and amplify it exponentially, like a dynamo generating electricity. Could the same process, acting over billions of years within the cluster's gently sloshing gas, take even a vanishingly small field from stellar sources and build it up to the observed strength? If so, then a primordial seed is not necessary. The field could be entirely self-made from the ashes of dead stars. Testing this is one of the hardest challenges in modern cosmology. We cannot go back in time to measure the infant universe's magnetism. Instead, we must look for indirect forensic clues. The Leo cluster becomes a critical laboratory because of its distinct properties, its well-mapped sloshing core, and its population of unusual galaxies. Scientists look for a smoking gun in the field's geometry. A primordial field stretched by the universe's expansion might show a preferred orientation on the largest scales, aligned with the ancient filaments of the cosmic web. A field built from astrophysical chaos would be more tangled and isotropic. By meticulously mapping the polarization of radio waves from thousands of background sources, astronomers are trying to trace the field's lines of force, searching for that primordial fingerprint. Another test lies in the cluster's farthest, most pristine regions. If the field is truly primordial, it should exist even in the quietest, most unevolved gas at the cluster's outer edges, where few supernovae have ever occurred. Finding organized magnetism, there would be a powerful argument for an ancient origin. The implications of solving this mystery are profound. Confirming a primordial magnetic field would revolutionize our understanding of the universe's first moments. It would provide direct observational evidence for physics at energy scales 1 trillion times higher than any particle collider on Earth can reach, offering a unique window into the era of inflation. It would also mean that magnetism is as fundamental to the cosmos as gravity or light, a basic ingredient baked into creation from the very start. The silent, vast field enveloping the Leo cluster may be the oldest thing we have ever detected, a memory in magnetic lines waiting for us to learn how to read it. From dark matter deserts to galactic ghosts and magnetic whispers, the Leo cluster stands as a grand cosmic archive. Its 25 unexplained phenomena are not isolated curiosities, but interconnected threads in a single, sprawling tapestry of mystery. The ghostly galaxy with no dark matter challenges the very scaffolding of our universe. The brilliant blue blob proves stars can ignite in the void. The silent, rotating hydrogen cloud asks if a galaxy needs stars at all. Each one is a doorway, and behind each door lies not just an answer, but a potential revolution in our understanding. These are not failures of observation, they are triumphs of discovery, revealing the limits of our current knowledge and pushing us toward a deeper, more complete picture of reality. They remind us that the universe is under no obligation to conform to our elegant models and tidy simulations. It is wilder, more creative, and more mysterious than we dare to assume. So we return to you, the explorer. Which of these 25 cosmic riddles captured your imagination? Was it the overmassive black hole in its tiny cage, the fossil radio bubbles of sleeping giants, or the primordial magnetic field that might remember the first moment of time? Share your thoughts in the comments below. Your curiosity is part of this journey. If you want to join us as we unravel more of the universe's greatest secrets, be sure to subscribe and hit the bell. Until our next voyage into the unknown, keep looking up. The cosmos